You've got exactly 20 minutes before your mock exam starts, and this curved graph, it's the ultimate Cambridge examiner chess trap. Seriously, if you're sitting the IGCSE Physics 0625 paper, this is the exact moment where your grade boundary is decided. You might think, oh, I know how to read a graph, but trust me, the examiner has designed this specifically to catch you completely off guard. When we first glance at this source graph, our brains immediately want to just rush through it, right? We just want to write down what it looks like. You see a curve going up, flattening out, dropping super sharply, and then flattening again. But look, in Cambridge physics, simple visual summaries just aren't enough. We have to really dig in, uncover the real story here, and translate this visual data into hard physics principles. So where do literally 80% of students lose easy marks on this exact curve? Well, most walk blindly into a massive grade boundary trap right here because they completely misinterpret what the changing gradient actually means physically. They look at a flattening line and say, oh, the speed is dropping. Actually, scratch that, it's entirely wrong on a speed time graph. They're confusing the shape of the line with the actual variable being measured. Okay, let's dive into this data table and decode the anatomy of this trap. This right here is your ultimate cheat sheet for motion graphs. You see, on a distance time graph, the gradient is speed. But wait, we're looking at a speed time graph. Here, the gradient equals acceleration. A downward slope means decelerating, so slowing down. A horizontal line means there's absolutely no change in speed, the object is moving at a constant speed. And hey, if they ever ask you for the distance traveled, you just find the area under the graph. So the absolute crucial point here is knowing exactly which set of rules to apply before you even write your very first word. Now, let's look at the data to see how this builds into the actual physics context. We really need to track the parachutist's true journey step by step. Ordinary revision absolutely fails if you just memorize the shape without understanding the underlying physics. We're going to connect the raw math of the graph directly to the physical forces acting on the parachutist as she falls through the sky. Let's start right at the very beginning of her jump. At point A on the curve, the line is super steep. Her speed increases rapidly, so she's accelerating. But notice how the curve starts to bend? By point B, her speed is still increasing, but kind of more slowly. That means her acceleration is lower. And that's all due to air resistance building up against her weight. Finally, she hits point C, where the graph completely flattens out into a horizontal line. Her speed reaches its absolute maximum value and stays exactly the same. This is it, terminal velocity. And because the speed isn't changing at all, the acceleration is exactly zero. And now we reach the critical junction. What actually happens when the parachute opens at point D? Well, in just a moment, I'll show you the exact examiner clue for this sudden drop that changes the answer completely. But first, you really need the framework that makes that exact clue completely obvious. Because honestly, just knowing what happens isn't enough. You've got to know how to write it down to secure those top band marks. When we look at the source mark schemes, this top-band framework emerges that lets you essentially checkmate the examiner. Whenever you're faced with explaining a complex graph like this, you have to use these 4 steps. Step 1, always state the core concept like terminal velocity or deceleration. Step 2, extract specific evidence from the data. Literally pull numbers or letters right off the axis. Step 3, apply your scientific reasonings to connect that data to the physics. And step 4, secure the whole shebang with precise, exam-safe wording. This structured approach literally forces you to hit every single requirement on the mark scheme. Notice how clearly this exposes the trap we talked about earlier. Spot the error in the flawed student answer on the left. The parachutist goes at a constant speed. Sure, okay, it's technically true, but it's way too vague and it misses the mark scheme entirely. It's conversational, not scientific. Now look at the top band Cambridge star response on the right. Reaches terminal velocity, acceleration is 0. See the difference? It perfectly executes our framework. It gives the exact scientific term and states the mathematical reality of the acceleration. For sure, that is how you guarantee your marks. All right, back to our trap on the graph. Take a quick second to visually locate the region from D to E to F. Right there at point D, the parachute opens and the speed decreases incredibly rapidly. And here is that crucial examiner clue I promised you earlier. Just look at the sheer steepness of that line compared to the beginning of the graph. This brilliantly illustrates the exact concept we need. That crazy steep downward slope from D to E to F, that's a negative relationship. As the values on the x-axis for time increase, the values on the y-axis for speed fall sharply. Physically, this represents a massive, high deceleration. The air resistance from the open parachute is now vastly greater than her weight, just throwing the absolute brakes on her fall. But the deceleration doesn't stay quite that extreme. As the curve flattens out around point E, her speed is still decreasing, yeah, but a lot more slowly. Her deceleration is lower. This continues until point F. Right here, the line is perfectly horizontal again. She reaches a brand new, lower constant speed. She's established a completely new terminal velocity where, once again, the acceleration is absolutely zero. She safely drifts at this speed until point G, where she hits the ground, slowing down rapidly to a complete stop with a very large deceleration. Let's test this with a real exam-style data extraction, okay? Imagine the question asks, for how long was the parachutist traveling at her new terminal velocity of 5 meters per second? Applying our data extraction math skills, we trace the horizontal line from point F to point G straight down to the x-axis. The flat line begins at 35 seconds and ends exactly at 60 seconds. So 60 minus 35 gives us exactly 25 seconds, meaning she was traveling at this lower constant speed of 5 meters per second for a total of 25 seconds. Easy, right? By breaking it down exactly like this, you've successfully evaded the curve trap. You aren't just looking at a random squiggly line anymore. You've uncovered the true physical context of falling, air resistance, and parachutes, and you're connecting them directly to the gradient changes on the speed-time graph. You know exactly how to extract the data, calculate the time, and deploy precise phrasing like terminal velocity and zero acceleration, completely securing those high-tier explanation marks. However, beware, the examiner has a secondary trap waiting, and honestly, it's even more dangerous. What happens when they strip away this beautiful, clean graph entirely? Well, they're going to force you to apply these exact same freefall and terminal velocity principles to raw, ticker tape, practical data. You'll literally be staring at a strip of paper with dots on it, and you'll have to calculate acceleration without a plotted curve to guide you. It's the ultimate test to see if you truly grasp the motion concepts we just covered. Right now, you've got the graph skills down, but you're still missing the critical calculation method for those tricky ticker tape practicals. This is the exact piece of the puzzle you need to ensure a flawless grade. To achieve total checkmate on this topic and ensure you're fully prepared for whatever curveball the examiner throws at you, you absolutely must click on our next explainer immediately. Let's finish building this exam strategy. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Because ultimately, the true test of physics isn't just reading a clean line on a page, it's whether you can still see the invisible forces of nature at play when the graph completely disappears. See you in the next one.